This problem has us find the reaction at A and the tension in the cable. And we are to treat A as a pin. So the reaction at point A and the tension I will be calling T in this problem as we go forward. So we want a free body diagram. We can also give some of the given information, although it will also be reflected. We're going to use a weight W of 80 pounds. Pounds is already a weight, so I don't need to convert anything there. And we have a pulley here at D that we will treat as frictionless. So for the free body diagram, we are going to need to choose our object of interest. Now, in this case, we have this rope here. If we look at the blue bar, we want to separate that. We need to know what's happening at A, so that pin itself cannot be included. We need to know what the pin does to our blue bar. And we need to know the tension in the rope, so we don't want to include the rope itself. So what I can do here is, for my object, I'm going to include, just so it's kind of a little bit clearer what's happening, I'm going to cut around there, and I'm going to cut around here. That will be part of my object. And then not the pin, but what the pin does will be in here. So this is basically my object. Just so it's kind of clear, I'm going to include just a little bit of the rope so I can see the tension in that rope. Or I could detach the ropes completely and see what their effect is. But this is the object that I am going to isolate and see what's happening to. So I have my bar here. I'm going to have just a little bit of the rope and a little bit of the rope here as part of my object. But where I cut, I'm going to be able to see what was inside that object. In this case, it's the tension of the rope, and we'll be seeing this again when we look at trusses. All right, so that's my basic object there, keeping just a little bit of the rope so I can see what the effect is. Now I need to know what are the forces acting on the object that I kept. I'll include my coordinate system here. And I have my point B. I have a point, this doesn't have a name, I'll call it E, and a point C here. So I have the tension from this rope that I cut through. Well, the tension in that rope is just going to be entirely caused by the weight of that cylinder. So we have 80 pounds acting down at point C. And we have, I'll draw point A over here. That's the only real external force we have acting. We're not compensating for the weight of this beam itself. At A, where we have that pin connection, as we've seen before with pin connections, we will have a horizontal component and a vertical component, and we allow for free rotation around point A, so we don't have a moment at A. We'll have a distance of 5 feet, 5 feet, and 3 feet for A to B, B to E, and E to C. All right, so the pin is taken care of, but now we still have these ropes that we cut through at B and at E. So at B, where I cut through that, I can now see the force that was in that rope, which is what we call tension. And as far as this object knows, that tension right there is straight up and down. The pulley is not part of this system that I'm looking at. It's still affecting the problem, but kind of indirectly. So what's happening is that rope is going from B up around D and coming back at point E. It's the same rope all the way through. And it's going over a frictionless pulley, which means that the tension in that rope is constant. Anywhere we cut it, that tension is going to be exactly the same. So I also have that T on the other side emanating from point E. So actually the tension in this rope is going to be affecting the bar twice, at B and at E. At B though, it's straight up and down, and at E, it's going to make this, they give it to us as a ratio triangle, kind of an odd one here, that the horizontal is 1, the vertical is 2. That makes the hypotenuse the square root of 5 then. So I do have a radical. I'll just use it with the radical here instead of finding the angle. I'm going to get the same numerical result either way. So at this point I have the complete free body diagram, and that's the trickiest part of this problem, is getting that correct free body diagram. because that drives the equations, and this is pretty systematic in how we're going to be writing these. Same pattern as we will always do. We have two sum of forces and a sum of moments. So out of habit, start with the sum of forces in the x direction and account for everything. I have my ax. Ay is only vertical. The first t is only vertical. I'll have my second t, which points into quadrant 2, so it will be negative in the x direction. And that'll be 1 over the square root of 5 times t. And the 80 pounds is vertical as well, so that will not be in this equation. I have one equation, two unknowns, so I'll move on and write more equations. Hopefully one of them will have only one unknown in it. In the y direction, I will have my ay, no ax. The first, at point B, I will have the tension pointing up. At point E, I will have the vertical component of that tension, so I'll have another t term. And then a minus 80 from the weight of the cylinder at the end. So this gives me two equations, three unknowns, and I have one more equilibrium equation left, where I will sum the moments about a point, and I know that's 0 because we're in equilibrium. Here we have at A a pin connection, so once again that's going to be the place that's going to be the easiest, the least amount of work to take the moment about, so I'll select A, the pin. So ax, ay do not appear in this equation. Their perpendicular distance is 0 to point A as their line of actions pass through A. So moving on to B, where I have this tension, I am going to have T is already vertical, and it is going to have 5 as its perpendicular distance, and this causes a positive moment around point A. I'll put a plus there just to remind us that we did already account for the counterclockwise or clockwise. So distance of 5 times t is counterclockwise positive. Moving on to point E, this tension is going to have an x component and a y component. The horizontal component of t is going to have its line of action pass through A, so that will not go into this equation. However, the vertical component, which will be 2 over the root 5 times t, has a distance of 10 feet from point A. And everything here will be in base units of pounds and feet. And that will cause also a counterclockwise rotation around that point. Just for illustration, breaking this down, I have the vertical component, that's what I just compensated for, and that horizontal component, again, which I won't because it has a distance of 0, perpendicular distance of 0 from point A. And finally, the 80 pounds at the end, vertical, has a perpendicular distance from A of 5 plus 5 plus 3 is going to be 13 feet. And that's going to cause a clockwise, or in this case, negative moment around point A. And by design, by selecting point A to take the moment about, we see that the third equation has only one unknown, t. So that's where I'm going to begin my solve step, is by taking equation 3 and solving it for t. So solving that, I get that t is 75 pounds. Now it's a rope, has to be in tension, but this does confirm that indeed the rope is in tension. It's possible that static equilibrium would not be possible in the system, so it's always a good check to make sure the things you think should be positive are, or if they're negative, that it's okay, or there's a reason they could be negative. If I take this result and go to equation 2, if I look up at equation 2, I have ay and t, but now I know t is positive 75, so ay is now easily solvable. And ay, I get negative 61 pounds. I assumed it was up, it was negative, so that means it's actually pointing down on this object. And then my equation 1. Once again, using my results from equation 3, because in equation 1, ax and t are my unknowns, but now I know t. So putting in 75 for t, ax, I get 33.4 pounds, and it's positive, which means my assumption that pointed to the right was correct. It does point to the right. and that's in pounds. So we got both of our reactions at A, the AX and the AY components. We got the tension in the rope, that one rope that went over the pulley there. So where we had to just be cautious in this one was in how we made the free body diagram, realizing that the rope from BD to E was one rope with one tension when we're in static equilibrium and when there's no friction, and we were told to ignore the friction at the pulley, which is typical for this class. And we had to compensate for the weight of that cylinder pulling down at point C. But when we put all of that together, we got what the tension was and our reactions with the correct directions.